What about your model? Does it poop?
Of course.
Big?
Big. Yeah.
How do you test it?
It's olfaction.
Your how is your model going to poop?
Well, let me give you. One project that we're doing right now is in the C. elegans. There is the muscles kind of push the food to the back. There's a very puzzling thing. There are kind of two lumps there and a little one in the middle, and the pulsing is different. Why is the pulsing different? We're trying to use the about 10 or 12 neurons from the C. elegans to understand the cycle. It's extremely complicated. So this is like the poop pumping.
Pumping in you, the pooping lemma.
Yes, the poop. So I mean, even the way the muscles contract to help the poop get to the right place is something people don't understand well enough. And, it's very exciting. It's very frustrating. We haven't got a solution yet. We have no idea why this is happening.
Well, if you have something intelligent to say about this.
Cyber pooping. Yeah.
Thank you very much for the talk. It was very inspiring. I see that many of you do interdisciplinary research, like, for example, in cybersecurity or in this case, biology. I do interdisciplinary research myself, and I would like, if you can give a good advice on how to do it properly, because it's very challenging to cope with other disciplines and to agree in, for example, how you want to model a system, how do you want to model human behavior, and so on.
First of all, be patient. And second, be aware that none of the camps you try to work with will appreciate fully what you do. So what you do is really believe in what you do. Now, the real truth, if you look at interdisciplinary, there are tons of chances, because the way you look at the question differ from, the discipline you came from. So, and therefore, try to re-ask the right questions. And then what David said is the right thing. Talk with people from both camps and see, their point of view, their language, and then reframe it. So that's my answer.
So I'll start with the technical solution to your question. So I think that definitely younger people, when they work in an interdisciplinary field, they have a risk for their career, because in each one of the different disciplines, they're pretty suspicious about anything that's coming from the other side. I think so. Practically, sometimes there are sub-communities that are doing the intersection. And if you can, I think it's the easiest to start there. And it's easier to bring to, let's say, from my point of view, we have a sub-community that does economics and computation.
At the beginning we did.
At the beginning we did it, right. So I'm starting with the easy thing. Sometimes you have communities, and once we have that sub-community, it's much easier to bring to that community both new ideas from economics and new ideas from computation when needed, and because that community is really built to combine them. At a certain point, that community can start taking back to the two parent disciplines, but that's always much more complex. So on the simple thing, if I'm a young person, what should I do so my career wouldn't suffer? If you can find the community, then you're lucky, and that's probably the easiest way. A much more difficult question is, suppose you're either young or old and really want to start a new interdisciplinary field and no one is listening to you, what can you do? And the answer is, it's difficult. You have to be a good time.
Get tenure first.
You have to get tenure first.
Or
well, you have to either get tenure or not to want to continue after your PhD.
I work with
in academia.
I work with psychologists, so.
Yeah, I don't need that. There are many things to say. My experience is, it's not always trivial even to find the one person you want to talk to in the other discipline. We've had frustrating cases where we couldn't understand what the biologist was saying, not because of them, because of us. And they were not even, I worked with a biologist, and for months and months, he didn't understand why it's not simply that what he tells us we put in a model and then it shows it. So what are you doing? I mean, you tell it to grow like a broccoli, so it grows like a broccoli. You can program a computer, he says to me. No. But it took them a while to understand that we're just programming the cells, And then you put 10,000 cells out there and they form a broccoli. That's a surprise. It takes a while, and there are people whom you can work with. It's a question of chemistry, no pun intended. And in terms of background, I don't know how many of you, probably none of you, are young enough to choose what you're going to study from the beginning. At least the things I've been talking about, studying biology and physics and computer science and mathematics, all kind of on equal par, is an excellent way to start. So I've had PhD students who came from computer science and had to do a lot of work learning the biology. I was a supervisor. I could say I don't know the biology. Tell me about it. That's my prerogative. And I've had people come in from biology, even after a master's, no computer science, no math, and they did the work, but it took them a long time. But people who came from a bioinformatics undergraduate degree or systems biology, maybe with physics, they did better. And you're right, it's difficult. You have to know more than one discipline and talk to people from the other discipline. A lot of talking.
Hi. First, thanks for the wonderful talks. And I have a question regarding the elephant and how do we know if it's an elephant, right? So
Pooping, we finished talking about.
No pooping this time. So basically you said like, okay, we are building this model and we have no specification, if I understood correctly. And then you say like, finally, eventually we should test it and realize if it's an elephant or not. And then you have an oracle in testing community, no? Like this expert who tells us whether it's an elephant or not.
No. I didn't explain correctly.
Okay.
You want to continue the question? Or
So my question was like, don't we have the access to the knowledge that the expert has such that we encode that knowledge in the model and we fool the expert?
Okay. So if that's the question, then what I just said was relevant. The expert knows that the pancreas will grow to be a broccoli. Okay? So what the expert does, it says, okay, start growing. It looks at the two rooms. The real thing turns into a broccoli. The model doesn't. So they know. But if the model turns into a broccoli, that's okay. What I thought you were saying earlier was we don't have an oracle who knows everything. We have an expert who knows a lot of stuff. And the expert's appetite about whether this is doing the right thing has to be satisfied in the test. It's just like if I'm the interrogator in Turing's classical test, I don't have to be the smartest person I don't have to be an oracle. I have to become convinced that this is the person and this is the computer. I can ask sophisticated questions and try to make sure. So there are experts there. The reason this is not verification is because when I build a model, I have no idea what they're going to ask. There is no specification. I mean, of course, when we start building an elephant, we know a lot of stuff, which we try to put into the model. But I don't know what they're going to ask. The interrogator can ask questions they do know the answer to, and questions they have no idea themselves. And they get an answer, does it seem feasible? How is it connected to the previous question I asked? Maybe I'm going to go back to my lab tonight and try it out. It's just like when I ask in the classical Turing test, I can ask a question I don't know the answer to. I just want to get a feeling for how the two rooms give an answer and then make my decision which is the computer and which is not.
Thanks for the great talks. So I had one question for you. You at the end you talked about mechanism design and you had a list of properties that you care about. I was wondering if you have thought about it from the point of view of synthesis as opposed to verification. So you just specify and the mechanism just gets produced.
Yes. So there have been some works exactly doing this kind of synthesis, saying, my goal is revenue, and here are the kind of things that I could do. Usually you limit it in some kind of to some kind of space, and then you search. Sometimes in just exhaustive search. Sometimes you can be a little clever and design new mechanisms. So there is a little work like that. I'm not sure that any of it reached. Well, yeah, there is some work like that.
I'd like. Could you say a couple of words about how you specify an elephant? So, what's the language you would use to? Does it look like a broccoli? What's the logic that one might use for that?
So, as I said, we don't build it so it looks like a broccoli. We try to. It's difficult. It's a very difficult question to answer because it's a lot of work. You don't just build a model and tomorrow morning. So we start out by thinking, and when I say thinking, I mean it's talking to the experts on pancreatic design, one thing I said to them was, you are a cell growing out of the gut, and you want to become part of the pancreas. What do you do? How do you respond to this kind of... So they say, well, there's this kind of signal, that kind of signal, depends if there's another cell right over here or not. And I say, tell me. They said, well, if there's another cell here, this signal comes in, then there's a 30% chance it'll split, 20% chance that apoptosis, commits suicide, and a 45% chance it moves to the right. So we put this in.
So how do you describe that property of looking like a property, looking like a broccoli? Is it a natural?
No, we don't. Just give me 2 more sentences. And so we put this in. You can write a program that says, I am a cell, 20% of the time I do this. If I get this signal, you write a little state machine or a little program. And then you put 20 such cells together, and they all fall flat. Something's wrong. So the biologist is with us. They say, oh, no, I forgot to tell you that you put in something else. Suddenly it starts getting a little bit like a bump. And this is how it's a lot of trial and error, a lot of wisdom from the biology side and modeling from our side. But it's very, very hard work. Now, if the thing doesn't look like a broccoli, they say, why is it a broccoli? What happens? And they say, well, there's this particular part here. It pulls in because the blood vessels okay, so we need to put some blood vessels. And it's like a bottom-up process where the ultimate goal is to see whether it looks like the real thing.
So my question was more on when the expert asks these questions, how do they express these questions?
So you're talking again about the end of the game, about the Turing test?
In that situation,
okay.
How do you describe
it's like
the
making a probe. It's like, one way to ask a question of a computer model is to run it under a certain set of circumstances. One way is to put in a question in model check and say, is it possible for this broccoli to move over there? And, you can ask questions in formal languages. And the same question you would ask the other one. There's this buffer. The team says, okay, they've asked us what happens if I do the following thing. I'll go to the lab, I'll do it, I'll give the answer. This Turing test is not a realistic thing. I mean, don't think that tomorrow morning we start... Don't try it at home. It's more like a philosophical point of view. But we had one case. Can I take 30 more seconds on this? We had one case where my biology, this was on the pancreas project, he got so excited by what the first videos looked like, he said, can you downgrade the graphics? I said, downgrade? We want to make it look... He said, no, I want you to make it blurred, kind of. I said, why? He says, because I want to show my postdocs this and the videos from the microscope, and ask them to tell which is the real thing. We didn't do it because there was technical issues, but he got excited just about whether his colleagues could guess what was the real... This is not a Turing test, it's not unexpected questions, but it's something to the effect that if they can't tell the difference, you're doing something right.
Thank you. There was another question.
So we all know that in the area of verification, that verification would be much easier if programmers would follow some simple rules, right? Making the program suitable for verification. But they don't do it. So the question is, how can we make progress in this direction? So which would be the right way to incentivize this? And maybe mechanism design has something to say, or not necessarily mechanism design, but maybe Danny has some ideas.
So from the point of view of incentive, I think definitely incentivize it, and I think that's
how?
The key. Yeah. So how, I don't know. I think it's it's difficult. I suppose that if you give some early and easy benefits, then people can do it. So, for example, unit tests are sort of like an example that at a certain point they reach the level where their benefit was seen by programmers, so programmers are writing unit tests now. Naturally, even though they really didn't like doing that, and if 20 years ago you told me that people would write unit tests, I would not believe you, right? So, I mean, the change can be done.
The point is, once the formal verification will be very useful, it can integrate and be part of the programming language in the future. Therefore, they will not have even a choice, because the way you program in the future will be, say, what you want are the properties, how you want to check it, and the rest will be automatic. So I don't, it's true that if I can force someone, it's great. If I can, enforce my will on that, it's great. I believe automation will do it once the tools are there. But just regarding what you talk about, remember for years we built programs that play chess. If you noticed last week, there was an AI program that taught itself to play chess. And
4 hours or
yeah,
something?
and it plays completely different the way any human being is playing chess. So, having man in the middle may produce nice elephant, but not really elephant.
Of course.
More questions? Mr. Noam?
Hello. My question is that you really advocate the use of formal verification, and I'm wondering what is your opinion about the definition of semantics for modeling languages? Because, for instance, for security, I don't know if engineers can bridge this gap between the semantics, and the same, of course, in biology is very clear.
We are left with no mind.
We actually have one.
So maybe I can say something brief, which has nothing to do with biology. If I'll allow myself to point you to a paper whose title is "What's the Semantics of Semantics?" And I think there, if you've seen this paper, so that we made an effort to explain that semantics is just so important you can't even think about.
Yeah, actually, I
verification.
have a friend who is a linguist, and she told me that there is also pragmatics.
Yeah.
And it's still not decided if pragmatics is a set of semantics or, but I mean, on a more functional. My
I'm
question
not
is more
quite
about
sure where your
day-to-day
question
practice.
is going to, but I think I don't have to tell anyone here that you can't do verification of anything unless you know what the semantics of your modeling language or programming language is, semantics of the specification requirements language, then you can start. The game can't start without semantics. It's like playing football without rules, without knowing who's the ball and who's the player.
And that's it. Once you have a system, you need to define what you want to do, what you want to achieve, and what is expected. And it will derive from there. You see, I don't see it bottom up, I see it top down. And therefore the semantics and the requirements and everything will be overall specification from which you will draw actually later on the programming, the models and everything. But again, it will be a paradigm shift. We definitely don't do the right job right now. He hates semantics.
So in terms of cybersecurity, classically there are proofs for protocols, stuff we are using. So where exactly, more concretely, would you think that our model checking, what we are doing, would come into play?
Okay, look differently. Let's say there are protocols out there, okay? And people wrote tons of papers all the years how one can produce a better protocol. Okay, my point of view is, okay, you have these protocols now, how you can improve it gradually. One of the ways to improve modules is also to say what are the expected properties and what should be done. And that can be formalized using formal modeling, and later on to integrate the verification that each model that out there will reach there. So I look at it with that respect as a gradual process to be taken in the near future. And it will be different from the way we do it right now. I don't have the answers. If I would have, you would see in the list of the projects. I know what I expect to happen in the near future.
One last question.
Returning to an elephant, so you told that you have a model of elephant.
I don't.
Okay, we suppose we have a model of elephant, but actually we have to take it within interaction with the environment. I mean, I think, for instance, if we compare an elephant in the room and the behavior of elephant of a model of elephant, elephant in the room might have some experience about the color of the walls in the room. So it might, let's say, do something unexpected. And how do you deal with that, and how far you are going in modeling the environment?
Let me bounce the question back at you. I mean, when you're building a human-made system, like an Airbus, you have to specify, before you start even doing the modeling, you know, what is the environment it has to be working in? Does it have to be able to work in thunderstorms or above the atmosphere? Yes, no. So this, I call this delineation. So before you start building your airplane, you're delineating what the environment will be able to, will not be able to, is relevant or not. Here too, when I come with my elephant, it's not just here's my laptop, it's an elephant. This is an elephant in a room, this is an elephant in a zoo. This is an elephant either in a room or in a zoo. So, and then the interrogator in this imaginary Turing test, they have to play the role of the environment. This is what's really going on. And you have to give them instructions, what you've modeled, what you haven't modeled. If they ask a question which is not in the model, they're not allowed to ask. Again, this is all theoretically, philosophically phrased here, but it's a good question. But the delineation ahead of time, this is horizontal delineation. What is your system? What is its environment? The vertical delineation I mentioned earlier, which is to what level of detail? Because suppose the interrogator says, what happens if I change this, this piece of DNA? I cut this, oh, I haven't modeled DNA. I stopped at the level of this cell. All these things have to be, the rules of the game have to be set up before the testing.
Well, in design of distributed system, a very critical question or problem or obstacle is so-called CAP theorem, consistency, availability, performance. What about mechanism design? What is primary concern in mechanism design? Consistency, availability, or performance?
I think that the current state of mechanism design is much more limited in the sense that there is no organized engineering field about large systems. Usually in mechanism design, we have a very simple scenario, and we're asking for pretty concrete questions of optimization. So for example, if you take what is probably the most complicated mechanism that I know about, which was this auction buying and selling spectrum, you know, it's pretty simple. It was clear we want to buy as much as possible spectrum and sell it to the new carriers. It was clear that we want as much reallocation as possible. It was clear basically what the constraints were. It was clear that we'd like to make more money for the United States government and that it would work. Not much more than that. So, and this is like the most extreme example of a mechanism that I'm aware of. So usually the mechanism design, we're not yet at the level of building very generic, very complex mechanisms, but more specific things. Now I have, you know, I'm Google, I want to set my ads and I want to make the most money. It's pretty clear. And of course, the engineering issues on the side, well, that's for the engineering side of Google, not for the economic side of Google.